So can you guys hear me? So while I erase this board, one thing I want to ask is when would be a good time for this coming week to have office hours? Now, I'll definitely have office hours Saturday morning. Well, I'll start with office hours Saturday at 11 o'clock in the morning. And that's the day of the exam, just in case you have last minute questions. But when would you want to have office hours during the week? Friday? How about Wednesday morning? So when are your review sessions? I know you guys have an exam on Friday, so I don't want to do anything Thursday night. Yeah, you have a quiz on Friday. Okay, so I don't want to do anything Thursday night, but when is do you have a review session for genetics? Yeah. When? And Thursday. Oh, you guys, so your Wednesday is free? Yeah, after the communication meeting, no. Okay, so then Wednesday at 8 o'clock, 8 to 9? Does that sound good, or is that too late? What's supposed to end at 8:30? What communication thing? What is this? At the Countway? Okay, so we'll make it at 8:30. So Wednesday at 8:30 is our office hours. What? 8:30 p.m. Yeah, here in this room. Is your communications meeting here? All right, so you'll just start right after that. Okay. Checking if Yetzo's here. Is that camera moving? I don't know. Hey, how are you doing? The hand up right there. Sorry. I guess that's tough to see a little bit. How's that? I gotta leave it dark because otherwise the video won't catch it. Okay, so let me just go over some administrative stuff. Of course, this is biostatistics, so any biostatistics class wouldn't be a class if there weren't talk about the different types of studies that were available for patients, such as case control studies, cohort studies, randomized clinical trials. This is obviously not going to be tested, so read it at your leisure, and I won't waste time rereading this to you out in lecture, so feel free to read it on your own, but you should know this. This is essential for you to know for the board exams. You need to know the different types of studies that are available and weaknesses and strengths of each. Okay? So this is a quick little PowerPoint presentation on these topics. Here's problem set 4. There's only one question because it's survival. And that's what we're going to focus on primarily for today, survival analysis, which is really the one thing that makes biostatistics unique from regular statistics is this focus on, hi? It'll be okay? Okay. What was that? Oh, well then that has to change. Okay. Thanks, Jessica. Okay. All right. And the last the last handout is I passed out the practice questions, and these are the solutions. And you can ignore question 2 because that has to do with regression. It's not on the exam. But if you want to look at it, that's just how to do regression analysis by hand. You should do these problems after you've gotten through the problem sets and have a good understanding of the material. Or if you don't carry out the algebra, at least be able to set up the equations. That's important. Okay? So that's where we're at. Today what we're going to talk about is we're going to quickly review what we went over yesterday, and then we'll talk about odds ratios, and then we'll talk about survival, and we'll spend a lot of time with survival, just going over some of the theory and everything. And then that'll be the end of the session. And the last 15 minutes I've prepared a little talk on regression if you're interested. And if not, that's totally fine. I'll just do it for the video camera. Okay? All right. Any administrative questions before we get started? So you know the exam is next week. It's on Saturday from 3 to 6. You get 3 hours for it. And you'll probably need all 3 hours. It's a lot of algebra. It's long. It's not difficult. It's just long. So, and yes. Yeah, that's if you really knew exactly what to do at if you didn't have to stop to think, it would just writing everything out would take 1.5 hours. So there's been a little bit of modifications of the test, and she's added some questions, so that's fine. Yeah.
Like, theoretically, if one were not to do any algebra, that things up,
I don't know. I haven't really thought about it. I mean,
how many questions are
there are 8 questions. 8 different questions, multiple parts each. So really, it's very comprehensive in the sense that it tests every topic that we've gone over. So I don't know the answer to that question. If you just set things up, so I wouldn't take a chance. You have to get the cutoff is usually between 70 and 75%. If you get that score, you'll pass. And I'll have office hours. I'll email those out, but I'll definitely have office hours that Saturday from 11 till whatever, 1 o'clock, just for last minute questions. And then I'll also have office hours Wednesday night here at 8:30 at night. Okay? All right? The exam is in this room for 3 hours. Remember, it's open book, open notes. Bring anything you want. You should definitely, I would recommend bringing that review sheet. And remember that review sheet is comprehensive. It covers all the equations that you need to know except for survival. So those equations, which we're going to talk about today, you'll just have to summarize those on your own. Okay? Definitely bring your calculator. Absolutely. You need calculators.
I don't know if you can address this issue, but if it's possible to order the tables, give us ordered information so we don't sit there having to order numbers on some of the non-target tables.
You mean order the tables on the exam?
If we're given the data table?
No, you can't do that. You're going to have to be able to order the data and rank them. Okay. So expect to be able to do that. Yes.
Why are we doing it this way instead of like ordering it as a computer tool?
As the what?
The computer tool, and it does the numbers for us, and then we can interpret it.
Because when you're reading a paper, you're not really using the statistical package. They're just giving you numbers. You need to be able to interpret what those numbers mean. and you need to know why they used the particular test that they did. You're right. If you were doing your own statistical research, you wouldn't be doing these calculations on your own. You would be using statistical software, which I think once you know the theory behind it is pretty simple, and you can pick it up anytime. But the real advantage of learning it this way is to be able to interpret what you read in the data, in the journals. So that's why. So you know what an analysis of variance is, you know what a t-test is, you know why they use a particular t-test. That's why. So, all right. So what did we do yesterday? We talked about trying to compare proportions. And one method was to use the binomial distribution and say that, well, when we're looking at proportions and we're using the binomial distribution, we can make the normal approximation as long as NPQ is greater than or equal to 5. And we can look at these distributions based on either the number of observations, where the mean number of observations that you would see is n times p, and the standard deviation is the square root of NPQ. Or you can do it based on the actual probability or the proportion. Like the probability of getting ahead is 1/2. So that would be your mean, and your standard deviation would be just whatever standard deviation here is divided by n, which you get to be the square root of p times 1 minus p over n. And when you're looking at for these proportions, you can do all the same tests that you would normally do that we talked about before. You can calculate 95% confidence intervals around a sample proportion using this equation, which is not new to us. You can compare one sample to the proportion of the entire population using this z-statistic, where p0 is the probability for the population. You can calculate the power of the study, looking at the overlap of two different groups, distributions, one being that of your sample, the other being that of your population. But the difference here is that you don't necessarily want to assume that both populations have the same standard deviation, so you separate them out. And we talked about that power yesterday, the power equation. This equation at the bottom, which got cut off here, it allows you to determine the sample size that you need for a study for a given power that you're looking for. Okay?
Sorry, that last one is under the binomial approximation normal.
Yep, binomial approximation normal, that's why you're using the standard deviation. The only difference between this equation that we used and the one that we did previously with the 2 power is that before we were assuming both curves have the same standard deviation, sigma naught, and here we're using different standard deviations. It's just a different way of doing it. Then, instead of making one sample comparisons, we talked about making 2 sample comparisons, comparing 2 different binomial proportions, where your null hypothesis is that the 2 proportions are equal, your alternative hypothesis is that they're not, and what you do is you calculate a pooled proportion, which is equal to this sum here, okay? And you use that pooled proportion to calculate the pooled standard deviation at the bottom of this z-statistic. It's very similar to the 2 sample t-test that we've done. Okay? Now I want you to ignore this equation. People use it sometimes, but another way of doing it is actually instead of using this standard deviation here, you can just use this one. So that's what I would prefer you to learn. Just copy this part of the equation and replace it for this. And that's the most common way of doing this. So you're comparing 2 samples. You can calculate a z-statistic. Why do we use a z-statistic and not a t-statistic if we're looking at 2 samples? Well, as long as NPQ is greater than 5, you can assume underlying normality. You don't even have to go through the t-distribution, right? You can assume that, and you can just go straight into the z-statistic. You can assume that your standard deviation, although it has an error, is normally distributed, not t-distributed. Okay? So whenever you're dealing with these binomial proportions and NPQ is greater than 5, always use the z-statistic. You don't need to. There's no such thing as using the t-statistic in this case. So that's how you would look at the difference and compare 2 different binomial proportions, but there's another method of doing it. And that method is using the 2x2 contingency table method. Looking at 2 independent samples. Remember, this contingency table method looks at 2 independent samples. Okay? And the null hypothesis says that P1 and P2 are equal, same as before. What you do is you construct a table where depending on what you're looking at, the observed variable is on the columns and the outcome is on the horizontal axis. And we've been through examples of how to set that up. But you look at A, B, C, and D of those observed values, and then you calculate the expected values based on these equations that we derived yesterday. And so the whole idea is that these equations, the expected values, are based on the premise that the two proportions are equal. Okay? So you would want to compare your observed values with your expected values. If they're very different, then you know that the observed values are not what you expected. And the way to do that is to do the chi-squared statistic, where you take the observed minus expected in each little box, subtract 1/2 from that just due to the continuity correction, square it, and divide by the expectation value. That's your chi-squared statistic. The number of degrees of freedom being the number of rows minus 1 times the number of columns minus 1. In a 2x2 table, that would just be 1. And you compare this to 1 minus alpha over 2 or 1 minus alpha? 1 minus alpha. Is it a one-sided or a two-sided test? It's a two-sided test, but remember, chi-squared, which derives from the square of a normal distribution. Okay? So it's a two-sided test, but because everything is just on the positive end, you're looking only at the 1 minus alpha. Okay? Here's a shortcut version to doing a 2x2 table. It got a little cut off, but I think you guys are familiar with that equation. You can only use this chi-squared test. Remember, this test is exactly the same as the previous test. You get the exact same results that you would in the previous test. But it's used more often in the literature because people like looking at tables, and that's why it makes it convenient. Because it's the exact same as the previous test, you can only use this test when the expected value is greater than 5 in each block. So these expected values, you need to check to make sure they're greater than 5. For the purposes of the exam, yeah, they will be. But just in real life situations, if it's not, you would have to use an exact method of calculation using what's known as the hypergeometric calculation. You don't need to know that. Okay? So you need to be comfortable with getting these contingency tables and making them. The nice thing about contingency tables is that it doesn't have to be 2x2. It can also be, any size, R by C. So you can compare multiple things. And then lastly, because the previous contingency table test, which is called the Yates test, involved independent samples, here's the contingency table method looking at paired samples. This is called McNemar's test, where in this quadrant, the upper left and the lower right quadrants, you have your concordant pairs, where you have matched samples. If the outcome was the same for both of them, those are called concordant pairs. In the upper right and the lower left quadrants, those are called the discordant pairs, where one individual in a paired match had a different outcome from the other. And then we went over the equations to use. It's actually a chi-squared test that looks like this. I went over a different sort of notation yesterday, so you should probably use the notation from yesterday and not the one in this handout. All you're doing is, if the two treatments or the two variables are the same, then you should be expecting that R and S are equal. The number of discordant pairs in each group should be the same. So that's what you're testing. You're seeing if there's a difference between R and S using the chi-squared statistic. Okay.
This works, you can call this, there's nothing wrong with it.
There's nothing wrong with this either. You can use this as well. So let's go to the board now and talk about odds ratios and how we look at odds ratios and what they mean and why they're important. Because in all these medical journals, what you want to do is you want to look at a disease, for instance, and see whether a treatment, you want to see whether it's associated with a particular risk factor or not. And so, take for instance lung cancer. You want to see what's the relative risk of developing lung cancer if you smoke versus you don't when you're not smoking. Well, you often report it as relative risk, but when we do all our statistical calculations, we use odds ratios. And most people assume that odds ratios and relative risks are essentially the same thing, but that's not always true. So let's go over what each of those are, the odds ratios and the relative risks, mathematically. So in epidemiology, right, we often want to evaluate risk factors and their relationship to disease. We can look at it very similarly to diagnostic testing, where we can have a disease, or we can look at disease, just say lung cancer, and either the person has it or they don't. And we can look at the risk factor, such as smoking. And either they do smoke or they don't. And we can label these boxes just like we normally do, A, B, C, and D. Call the total value N. Okay. And for now, let's just say that this sum is A plus B. Well, actually, forget it. We don't need to do that. But we know that A plus B is the total smokers. C plus D are the non-smokers. A plus C, that total, are the number with the disease, and B plus D are the number without the disease. Okay? So let's define some terms here. The prevalence of the disease. What would that be equal to? Yeah, it would be A plus C over N. And what would be the prevalence of the disease in the exposed group, which I'll define as this probability P1. So what would that probability be? Prevalence in the exposed group. A over A plus B. A is the number of people in so the exposed group is this top row. A is the amount with the disease. So A over A plus B. And the prevalence in the unexposed, I'll call that probability P2, and that will just be C over C plus D. Well, the relative risk is just defined as this ratio of P1 to P2. Okay? That's all it is. It's the prevalence in the exposed group divided by the prevalence in the unexposed group. Okay? That's the relative risk. And so if you want to look at the calculation, it's just A times C plus D, okay, over C times A plus B. Okay? That's your relative risk. And it's a very intuitive term. Like if the relative risk is 3, that means that you're 3 times as likely to have the disease of lung cancer. You're 3 times as likely to have lung cancer if you smoke than if you don't smoke. It's very intuitive. But it's not very mathematically convenient. I mean, it involves these summation terms. How do we know what A plus B is and C plus D is relatively in the population, right? What the smokers are and what the non-smokers are. I guess we know smoking. I mean, it's about 1/3 of the population are smokers. But a lot of times we don't know what the true ratios are of these numbers in the population. So it's hard to deal with. That's why we look at odds and the odds ratio. So first, let me define what odds are. Okay? If I were to ask what the odds are of the disease of lung cancer in smokers. So the odds of lung cancer in smokers, it would be equal to P1 over 1 minus P1. So it's the ratio of the probability of having the disease divided by the probability of not having the disease in just that one group of smokers. And it turns out very nicely because P1 is just A over A plus B. And 1 minus P1 would be B over A plus B. Right? 1 minus this is just B over A plus B. And the A plus B's cancel out and you're left with A over B. And similarly, the odds of lung cancer in non-smokers would equal P2 over 1 minus P2, which when you work that out would be C over D. So it's very convenient to make these calculations. If I were to now define the odds ratio, that's just equal to the ratio of these two values, P1 over 1 minus P1 divided by P2 over 1 minus P2. Okay? And when you calculate that out, that's just equal to AD over BC. Now the odds ratio is less intuitive, right? Because just the whole idea of having an odds, right, like, is weird to take this ratio of the probability of having the disease over the probability of not having the disease. It's not necessarily intuitive. It doesn't give you that good feel that the relative risk does. But if you're to do the calculations, one can show that the odds ratio is roughly the same as the relative risk if the disease is a rare disease. Right? Because if the disease is rare, then what do you know? You know that B is much greater than A, because this is the disease column and this is the non-disease column. And you know that C is much less than D. If you look at this equation for relative risk, if A is much less than B, the A will just cancel out. And you can ignore the A and the C, and you're left with the odds ratio. So that's where I'm working towards. See, in theory, if these proportions fit the proportions of the population, then everything would be fine. Not often. Often, most studies don't do that. They don't fit the probability of the proportions, but you'll still calculate the same odds ratio. And the idea is that as long as this disease is a rare disease, that odds ratio is reflective of the relative risk. So, all I'm saying is that for a lot of rare diseases, you can make the assumption that the odds ratio and the relative risk are the same. So you can work with the odds ratio and think of it sort of as a relative risk. Okay. Why do we want to work with odds ratios? Well, it turns out that it's much more mathematically convenient, and the reason why is because the natural log of the odds ratio tends to follow a normal distribution. So this allows us to look at the error of the odds ratios, the confidence intervals around the odds ratios, that sort of thing. What was that? Oh, yeah, sure. Okay. And so we always work with odds ratios in statistics just because it allows us to manipulate the numbers. Relative risk doesn't do that. When we look at the natural log of odds ratio and it comes out to be a normal distribution, the standard deviation, and these calculations can all be derived, but the standard deviation turns out to be 1 over A plus 1 over B plus 1 over C plus 1 over D. The square root of that. So this is the equation that we use to calculate our standard deviation, or oftentimes it's called standard error, on the natural log of the odds ratio. So this is the standard deviation around the natural log of the odds ratio. So if you want to calculate 95% confidence intervals around the natural log of the odds ratio, what you would do is you would say it would be the natural log of the odds ratio of whatever sample you're looking at, plus or minus 1.96 times this standard deviation. Okay. And now what if you wanted to take that and just call those numbers C1 and C2? What if you wanted to take that and find the confidence interval around the actual odds ratio itself? What would you do? So the 95% confidence interval around the odds ratio would just be equal to e to the C1 power and e to the C2 power. If I were to give you a little bit more intuition about where this came from, this term, the standard deviation, I would just, I guess, refer you to calculus. Oftentimes, the standard deviations are related to the first derivatives of functions. When you take the natural log of a function, the natural log of d dx, and take the first derivative, that's equal to 1 over x. So technically, this is just an approximation to the error because you're only looking at the first derivative, but it should be full of multiple terms of first derivative, second derivative, third derivative, and so on. You Taylor expansion, that sort of thing. But this is definitely a good, good approximation. Yes.
You have A and B really big, and you know almost, let's say, I'm sorry, C and D really big. You know almost nothing about the people who really close. You just got your sample, still have a big confidence ratio.
I'm not sure what you're saying. Well, let's get back to it. Let me finish the example. We can talk during the break. Okay, so I'm just trying to give you an intuition as to where this equation comes from without deriving it. It's called hand waving in physics. Okay, so let's do an example. And just say we have 263 people at a picnic. And a large group of them, oh, you have a question? Yeah.
I just don't understand what varies to create the normal distribution. What is that? What's on the axis? Like it seems like OR is a number, and so I understand having confidence or not having confidence in the number. But when we're dealing with like a statistical sample where it's varying sample versus something, I don't understand what the OR is varying compared to.
Oh, I see what you're saying.
Like what x if you were going to do e to minus x squared.
No, I mean, that's, so if it's a normal distribution, I mean, on the x-axis are your values of the natural log of OR, of the odds ratio.
So what's varying between the different ORs?
Just repeating the experiment over and over again, right? So
Okay, so
you do one experiment.
You got a data set of many times you did this experiment with
Right.
a certain population.
Well, you don't even have to do it, right? Because once you do one, then you can calculate the error on that one value. But in theory,
Okay.
right? Does that make sense?
Yeah.
Okay. But in theory, yeah, that's where this derivation is coming from. It's the idea that you set up one table, figure out the odds ratio, set up an entirely different table, like do it multiple times, calculate all the odds ratios, look at the natural log of those odds ratios, and that those values follow a normal distribution. Okay. So you don't have to do it multiple times.
Assuming that all my time. I mean, assuming that all the experiments were not. Right.
Yeah, I mean, you're confident in your data, and you set it all up, you get all these multiple odds ratio values. The natural log of the odds ratio follows a normal distribution. with this error. So then when you do another entirely different experiment and do it only once, you don't have to do it multiple times. You know what the error on that value is going to be to the 95% confidence. Okay? All right, good question. So let's say you have 263 people at a picnic, and there's a little bit of gastroenteritis going around. Fun stuff, especially for you people going into ID. So either they do get the gastroenteritis or they don't, okay, of those 263 people. And you want to see whether it correlated to them eating a particular type of meat sandwich. So did they eat the meat sandwich? And that's either yes or no. Okay? And let's say these are the numbers. Of 113 people who did get sick, 109 had the meat sandwich, and 4 did not. Okay? Of the 150 remaining that did not get sick, 116 had the meat sandwich, and 34 did not. And so the question is there an association between the meat sandwich and the gastroenteritis? And actually, more specifically, what do I want with association is, let's calculate an odds ratio. Okay. So the odds ratio of this sample is going to be AD over BC, right? That's just going to equal 109 times 34 over 116 times 4, which, when you get that value, it's 7.99. Okay, so no big deal yet. But the question is this odds ratio significant? And when I ask that, is the odds ratio significant, what do I mean? What am I comparing it to? 1, right? Because if the odds ratio, if your confidence interval around the odds ratio contains 1, then it's not significant at all. That means the odds are 1 to 1. Okay? So that's the question. Is this significant? Is this odds ratio significant? And the way to do that is just calculate the 95% confidence interval. We don't calculate it directly around the odds ratio. We have to do it around the natural log of the odds ratio. So the natural log of the odds ratio plus or minus 1.96 times this error, 1 plus A over 1 plus B over 1 plus C over plus 1 over D. And you can fill in the numbers. The natural log of 7.99 plus or minus 1.96 times the square root of all of these numbers, 1 over 109 plus 1 over 116 plus 1 over 4 plus 1 over 34. So that's how you would carry it out algebraically. And what you get is sparing you from the math, you get this confidence interval 1.010 and 3.146. So is it significant? Why? You guys fell for the trick. We're not done yet. This is the confidence interval around the natural log of the odds ratio, right? We have to get the confidence interval around the odds ratio. So the way to do that is you take e to the 1.010 and e to the 3.146. And when you do that, you get that the confidence interval is equal to 2.75 and 23.24. So is it significant? Yes, you're right, Steve. Yeah. So don't forget that last step.
Is this related at all if you did a test to see if there was a correlation? And then you figured out the top line and then p-value associated with that?
Which test are you talking about?
If you just do a regular proportion. See if there's a correlation.
Oh, if there's a correlation between the two? Yeah, certainly. The math works out that if you find that the odds ratio doesn't, in confidence interval doesn't contain 1, then that's the same thing as if you had carried out a 2x2 contingency table or a binomial proportions comparison showing that the two are not the same proportions. So you'd get the exact same result. Yes?
I think we're getting, you can just do this the other way too, right? I mean, you could do one, adding two zeros is 1.96 times the whatever and get the 95% boundary times the size.
Absolutely. You can do it totally the other way. You can use the chi-squared method that we had already gone over. You can use comparing the two probabilities using the normal approximation. That's totally fine. This is just how it's often reported in literature as odds ratios. So, especially with diseases, people like to hear odds ratios, like what's the odds ratio of developing the disease with this risk factor or without. People like just one easy number to remember, I guess. Okay, is this clear?
Like I'm throwing new information prevalence very well. It's very rare to see.
Actually, it's done all the time. This is totally fine. You don't have to assume anything. The only thing that you assume with the prevalence, when the prevalence is low, is that the odds ratio is equal to the relative risk. But you can still calculate an odds ratio anytime you want. Yeah. Okay? So there is a practice problem. It's the last problem on problem set 3 that just goes over doing this. It's important so that you understand how they calculate odds ratios and the errors on odds ratios. Now, one last interesting thing, which I'm not going to go over the math, I'm just going to go over the concept, is looking at multiple tables of odds ratios and understanding, can those tables be combined? So if you have multiple 2x2 tables, the question then becomes, can we combine the data? So let's look at an example. So just say you have one department in college that out of a pool of 15 male applicants and 15 female applicants, accepted 5 of each and declined 10 of each. Okay? And so what would be the odds ratio in this case, being male to female? That odds ratio for that would be just 1. We calculated out AB over BC. So that's department number 1. Now you look at a second department. Do the exact same thing. Male, female, accept, decline. Out of a total of 15 men and 75 women that were applying, they accepted 1 man and 14 were declined. They accepted 5 women and 70 declined. The odds ratio, again, is 1. Right? Now let's just take those two tables and just add all the data points up. So accept, decline, male, female. 5 plus 1 is 6. 10 plus 14 is 24. 5 plus 5 is 10. And 10 plus 70 is 80. And when you calculate the odds ratio here, it's 6 times 80 over 10 times 24. And that's 2. So what happened? This is called Simpson's paradox. And it just goes to show you how important getting these relative proportions within the population correct can be when you're looking at, when you're doing multiple studies and you're trying to combine your data, what's right and what's not right. So there is a way of combining 2x2 tables from different centers, from different data, and it's called the Mantel-Haenszeal method. And we're certainly not going to go over it. It's just too involved, and I'm just throwing it out there just so that you guys are familiar with the name. But this is a method used to combine the 2x2 tables and get what's known as a summary odds ratio. Okay? And it uses weighting. It weights the different data depending on how many people are there in each center, and weights it. And if you were to use this method to combine the two tables, the net result, the summary odds ratio that you would get would be 1. So just know that it exists. Know that it consists of 2 steps. The first step is that it looks at the ORs of the odds ratios of the separate tables and see if they're homogeneous, see if they're the same statistically, so that they can be combined. And then the second step, the last step, is just combine the tables. So, it's a 2-step process. Most statistical software packages will do it, and it's just one quick command, and it'll combine all the data. Okay? But just know that it exists, and that when you see in a paper multiple tables, it's not that simple just to combine the data. Make sure that the people who are doing those studies are doing it the right way. Okay? You guys set on that? So let's move into survival. I think this is the funnest stuff. It's very cool to compare different survival curves and understand, especially if you're interested in oncology, just understanding how different patients with particular cancers do on different types of treatment. But it's widespread throughout all of medicine. And so let's talk about it. We'll start now and we'll go through it for a little bit, then we'll take a break. Should take probably until 5 o'clock just to go over survival. So, survival analysis. By the end of this hour, you guys should know how to do 4 things. 1, determine incidence rates, or they're also known as hazard rates. 2, calculate and plot survival functions or survival curves. 3, find the errors on survival curves. And 4, compare two different survival curves, which is the most important because this is the one that's used to see if a treatment works or it doesn't, if it improves survival. Okay?
Say, find the error, you find the confidence intervals.
Yeah, the confidence intervals of the survival. That's what the goal is. Let's start a little bit about the theory first on survival. So, let's talk about this idea of incidence. And incidence really is the same thing as hazard. Because when we're talking about disease, it's the hazard is just the incidence of the disease. Okay. And so do you guys remember what incidence is? What is incidence? Yeah, it's the number of new cases that develop over a given period of time. Okay. So there's that added time element. What we can do is we can define what's known as an incidence density. Some books call it that, other books call it a hazard rate. And that's just equal to the number of cases or events per total people and time. So it's per time and per person. So for instance, there are 7 new cases a year per 1,000 people in the population of Crohn's disease. Okay? So something like that.
Is it for people in the population without the disease or for people in the population who have it?
It's usually defined as with those who do not have the disease. Okay. So if we were to look at the theory, and I mean, let's just call this lambda for now, because I'll use that variable. And just say, let's take an example where lambda is a constant. Okay. Which is not true. Like, over time, as you age, for instance, age itself is an added factor that makes the hazard rate go up. Yeah. As you get older, your rate of prostate cancer goes up in men. So, what if we just assumed that it was constant throughout time? We would develop a differential equation where the change in the number of people, we'll call it x. X is the number of people who, let's see, well, how should I call it? Let's say the number of healthy people in the population. The change in x over the change in time is proportional to this hazard rate, lambda, times the total, it's a density, so you have to multiply it by the total number of healthy people to begin with. And it's a negative value, right? Just because the hazard rate is how many people develop the disease, so it's going to be negative because the number of healthy people go down. Okay?
So this is the only disease.
Oh, I mean, even if we're just looking at this one disease, we don't have to. We're just ignoring all other diseases. So we can derive this differential equation, and I don't want to go through the derivation, but what you end up with is a function of the number of healthy people, okay, equal to the initial population that you're looking at times e to the minus lambda t. It's just an exponential decay.